Well, hello everyone, and Happy New Year. We're all a little fatter and a little older, and we're back here at the New Electric Workshop in Amsterdam, getting ready to move on our projects. We have the 818 that needs building. We have our Delta Flyer that needs tuning to make a little jaunt across the English Channel. We have a cabin cruiser that needs a diesel out and some warp loving in. And of course, we have some updates on actions going along the way. Like for instance, we have two ships coming into Rotterdam at this very moment, converging on the port and bringing us a new load of CALB CA series cells. We'll now also be carrying the 40 amp cell, which is interesting if you're looking at, for instance, the Siemens voltages, the DMOC voltages, 3 to 400 volt, 100 to 120 of these 40 amperes, and you have a lightweight system that will give you the juice when you need it. But we of course also have the 60 amps that would work very well in the same setup, the 100 amps that'll give you the longer range even, or the 180s that are more likely to be used in your lower voltage systems or in big ass boats like we like to build. Anyways, we'll be having a fresh load of CALB CAs on hand here in Amsterdam, and we're getting a good dose of Siemens and DMOCs and other EVTV components, so we have those on hand for you as well. Interest has definitely been picking up since Christmas and beginning of the year. Seems to look good, so we will be putting together a next shipment hopefully early this month and have it over by February. Hit us up if there is anything you would like to get your hands on here in the EU. For this week, I want to take you back to just before Christmas though, because New Electric visited the ECC Repenning GmbH company in Germany. It's just beyond Hamburg in Geesthacht. I hope I'm saying that right, probably not. It's about a 5.5 hour drive from Amsterdam, where ECC has their spanking new factory where the actual particulate matter and substrates come in, and they process the whole thing and they make these cylindrical lithium iron nanophosphate cells. So it's a relatively local production of this favored chemistry in an interesting cylindrical form factor. So we visited the ECC factory and took a tour of the facilities there. So here's our tour of the ECC factory building that opened this last March 2013. We were received in the lobby and shown some of the historical projects they had worked on, like batteries for bikes in the German postal unit, but their main product is this 48 volt units of 2 kilowatts 16 cells that are used in grid connected backup situations, mainly for renewable energy sources, shaving the top and low end of the loads. We were then shown the new production facility on the inside. Capacity here in this production line is 40 megawatt hours a year, and there's internal space to double the lines and bring it up to 80 megawatt hours a year in this single facility. Everything is done in-house, from mixing of the slurry in this proprietary mixing machine using solvents that creates a very fine and very equal mix of material that is then deposited onto the copper and aluminum cathode and anodes. The 85% of the solvents are then recouped through different ovens and distills to ensure that they get used again and again in the production process, and thus limit also environmental output of the factory. The two different sides are basically rolled together with a separator and stuck in an aluminum can, but there is a lot of automated quality control in the form of x-rays and cycle testing, which they proudly claim is twice the industry standard. So up to 5 full cycles per cell is tested instead of an industry standard of 2.5. Also on site is development of new lithium titanate cells in conjunction with BMW that will be used for starting next year's next generation product. Here's a little fork lifter with a 2 kilowatt 48 volt system and ECC BMS. And also here's a server room rack setup that holds 2 kilowatt units in a grid connected backup situation where you also have a PLC doing automated control of charge and discharge levels. So you can see these babies come from a very quality controlled German Grundigkeitfabrik environment. So the process by ECC is being very much controlled from the ingredient level as it comes in to the making of the slurry, the checking of the quality on the cathode and anodes, and then really automating all the processes in lithium iron nanophosphate batteries that would otherwise still be by hand. We saw a couple of weeks ago in EVTV, we saw a video, I think from the Rev Electrics guys, showing some battery manufacture. There were, a couple of steps along the way there where you were thinking like, hey, okay, this human quality control is interesting, but could that not be automated to a higher level of consistency? Well, that's exactly what they're saying at the ECC factory that they've done. And by doing it this way and by checking each cell over 5 full cycles and then grouping them into individually balanced groups for sales, for packs of customers, for power backup units, what they're doing mostly there in Germany. And that way they feel confident on giving much longer, up to 7-year warranties on cycle life. So that's how they make their quality. After the tour, we got a chance to talk to Dr. Reipenning himself, the founder and builder of the factory and owner of the company. And he had some interesting things to say. Let's check it out. I believe your first interest in starting this company and starting the battery storage was aimed at a grid power supply storage and backup?
Yes, that's right. Grid power supply storage for on-grid, off-grid systems, for power, for low peaks, things like that, much more.
So be able to shave the high peak and
yes, the low peaks. If you have low consumption, you can charge the batteries. If you have high load or high power peaks, you can equalize in the grid.
And at that time, had you always considered or also thought that the mobile application would be interesting for your product, or?
Yes, it is of interest, but mobile is always a long way with all the homologation you need, yes, with all the safety questions, things like that. We are inside the German automotive industry for developing. We have other projects with much more private partners for electrical cars, for electrical boats, even a power boat on the Bodensee. So we are, but this is much more a long way before. And the question is if you take the full EV or the hybrid systems, so you can go both ways for the future.
We were thinking, hey, this is an extremely interesting product because of the gravimetric
gravimetric energy density.
Absolutely.
In it. Yes, it's not more. It's not less than with the NMC, because for NMC you need a lot of safety measurements, and even our cell we have about 130 to 140 watt-hour per kilogram, and that is quite a lot. It's similar to that what you can get in NMC today, but with NMC you need a very safe containment.
Absolutely.
Around.
So the weight and the cost of that.
The cost, the weight, so yes. And this is the principal advantage of lithium iron phosphate.
Also in the NMC cells that we now carry, we see there is still a venting mechanism, whereas in the cylindrical cells that you produce, I see there is no more venting mechanism needed.
No, it's not needed because you have no gassing problem. And even for future, only to mention it, the LFP is the one side, and the next one for future will be the LTO. LTO has a very low energy density, but has the highest power density in all for all lithium-ion systems. And if you go into the hybrid system, you need at a very, very short time the recuperation of the energy, and therefore LTO will be one of the most promising for the future.
Right. Also maybe for the fast charging.
For the fast charging, for safety, it's absolutely safe in comparison to each other system, and it has the highest reliability and cyclability in all. This will be one of a future product too.
And now that you've mentioned the Titanet, do you feel the roadmap towards that product? Is it a 5 to 7 year?
No, it's next year. Yes, we developed already the material, and we tested in laboratory tests cells with partners like Fraunhofer Institute, and they found out that we have the best material in the world now, because even Titanet has a problem of gassing. And we solved this problem with some surface treatment, physical plasma treatment, and have no gassing. And therefore we have a cell which has no gassing, has long life, things like that. And we will scale up in the roadmap next year the lithium titanate at a reasonable price. That is the other point.
Of course.
Titanate is very expensive, and we will come to a reasonable price for the market.
If we would take, say, a fast charger, the modern fast charge, Tesla, 120 kilowatts, now we're talking about 6 to 7 C, and I'm thinking possibly this is more for the Titanet cell than...
Yeah, it's much more for the Titanet, and the big cells we have warm up.
Yes.
So for that application, it's sometimes better to have smaller cells to dissipate the heat better.
Yeah.
So you see, we have in comparison large cylindrical cell which stores the heat very good.
Yes.
That is a little small disadvantage. And continuous charge, it's much better for the lithium titanate, not to impact the reliability too much.
Yeah. I prefer BMS strategies, the monitoring versus managing strategies.
Yes.
And I've heard from Henk that the current BMS, it monitors and it flags, but it doesn't actively try and balance individual cells.
Yeah, we have something like an active. It's much a passive one, but you can adjust the current between 0 milliamp to 800 milliamp. So it's like an active balancing. But we hope normally we don't need too much balancing on our cells, because our we scatter only less than 1 amp hour per cell, so they are very tight together. That is the normal case we see, and the balancing is very fast.
Yes. Well, this is what I found. The first 4 cells that I had out of the box, I did 3 charge discharge. I had less than 0.02 volts at the outer edges. So for what I would consider my norm, these cells out of box are both top and bottom balanced for how we use them. What I was interested in, being so advanced in the technology, we haven't really found a mechanism by which cell drift can even occur. Only if parts of the pack are at different temperature than other parts of the pack. This is the only way I've found, or faulty BMS, because it draws. It's parasitic load. It's trying to save, but it's destroying. So I was wondering if in actual fact you find cell drift, and if so, why? What is the reason for cell drift?
But you're right. It's always a temperature.
Always so.
It's always a temperature. With temperature you have a change in internal resistance, and with internal resistance you have another current, another voltage in it. But it's not too much. It depends on the temperature in which you are working. If you have a very low dependency, if you are in temperature higher than about 25, 27 degrees, so you have a small scattering of temperature even to 40 degrees, but under 25 degrees you have always a steep increase of resistance, internal resistance, but with the internal resistance, you increase the temperature and you can equalize a little bit. And this is always a problem. In lower temperature region, you have more problem in disbalancing of the cell than in higher temperature.
Absolutely.
Because the dependency of the internal resistance is very high.
And what we found that even in an application where there is daily use, say after 6 months, the amount of cell variation is still so tiny that if the vehicle sees at least maybe once, maybe twice a year a service station, the investment in active balancing plus the chance it goes wrong and actually hurts is more of a risk than having pack level management plus 6 months checkup.
And you have this one, what you is 5 parallel cells. And the 5 parallel cells adjust themselves.
Correct.
That's always the way.
So
if you have here one in the middle and one outside, so you will always equalize over the whole stack.
So if I were to say to you, say in America, we would like to take 50,000 amp hours in reserve, be able to help individual customers, tell them they must use in a system this way, have at least warning light and a system cutoff at 2 levels, plus somebody they can come service at. Would you feel comfortable if we repackage your products and have them used this way without active balancing?
I think so, yes. The best is you even will have for one parallel syringe only one BMS, I assume, yes? So I think it should work, yes. It's a question if you will sensor each cell's temperature, you will do that?
Well, this is what I was wondering. The next question would be, would you be comfortable with only voltage level, or would you want the combination of voltage and temperature level?
I always would recommend to take even the temperature level.
And wouldn't that be suffice? Because for us in a boat, we will always be doing whatever the parallel is, it'll always be 15 in series, to say under the 50 volt. If we would be monitoring the temperature per module, per box, and we say in our PLC unit, if any box is more than 2% higher or lower than any other box, warning light. Any box more than 5% higher or lower, system cutoff. Would that be comfortable, or would you want individual cells still?
Normally we have individual cells. That's what we have today with individual cell. For me, it's a question of maybe individual cell, but one syringe parallel, maybe a compromise.
The parallel line would be okay.
That would be
That would be okay.
To avoid any risk.
Right.
You have the deep discharging of the cell, and with deep discharging, it's always difficult to charge them from outside. You have to do a formation act on it, because with deep discharging, you have always the risk of copper release, of copper corrosion, and if you try to charge it, you will have a copper deposition on the surface of the electrode. And it is always, I have seen it sometimes from customers who have such cells. They have a deep discharge and try to charge it. And the cells have been, the electrode surface was full of copper, because you have a copper release, a copper corrosion, and with the charging, the copper was plated on the surface. And this is always the problem with deep discharge. So you have to do a very, very smooth formation to avoid any risk of short circuits inside the cell.
Will this even be after the cell has been formatively charged the first 3-4 cycles? It's been well formed. Would it discharge? And to you, what is anything under 3 is deep discharge, or under 2.5?
The risk is under 2.2 or something like that, not 2.5. But if you have it in this region, and you have the self-discharge, you will fall down.
So say if our bottom balance procedure would be to discharge to 2.7, but under tapering current. So you come down at 40 and towards 2.8, we're tapering, and then we taper down to 5, and then it will just not bounce up above 2.8. It'll stay about 2.79. And this is where we observe them, and if nobody is dropping, this is a pack. Now we bring them up together. That's generally
that's Good, yeah.
It's okay. Thanks.
Yes.
Well, hey, I'm just buying stuff.
Yeah,
I
fine,
make
fine,
it,
fine.
so
It's,
you
all,
make
it's very fine, fine work. They have to come consistent to use, that you can put it into your electrical design.
Plug and play.
And this is what I was...
a little plug, and then play.
Well, thank you very much, sir. This is, we live for this stuff. We're really enthusiastic.
So
like you can see, we're not building for nothing.
Thank you. It was a nice discussion. Yes.
Yeah.
Thank you.
So, excuse my very basic interview skills. Got a lot to learn on that front. But it was definitely a very interesting meeting, Mr. Repenning. And to sum it up, after he gave some background information on ECC, we talked a little bit about those Titanate cells coming up with the very high C charge and discharge capacities, the safeties, the gassing. But to me, the most interesting point was our conversation as it came to the BMS and balancing issue. He did concede that their BMS strategy involved a 0 to 800 millivolt balancing capacity in those boards, but that in actual fact, he never saw or hardly sees the need arising to do this balancing, so there's hardly any cell drift. His point seems to be the cell drift can only really occur under temperature variance if you don't have a parasitic load on a little section of the pack, but are only drawing on the pack as a whole. So I felt it was a boon for the EVTV patented bottom balancing and monitoring versus managing strategy of cell care. That he conceded that as long as we would do a parallel series and monitor temperature and voltage, and then have a flag event at a 2% variance over a check of different quadrants, and then a shut-off event at maybe a more than 5% variance, that would be comfortable for him to repackage the product in that way. Well, I'm reading that as that we would still have warranty when use the product in that way. So that's an interesting point to get from the man building the factory, I thought at least. I also thought it was interesting, his concerns about charging when under 2.5 volts. That also seems to concur with the settings on, for instance, our PowerLab 8, which automatically has this under 2.5 volt, 500 milliamp max charge level, bringing up the cell to this part where it can then really accept the electrons again. Anyways, I should probably stop talking before I start trying to type myself smart on these issues. It was really fun visiting the ECC guys, and we are talking to them about outfitting the Delta with a little over 30 kilowatt hours of these cells for our cross the channel experiment. That would mean that we have 30 kilowatt hours with the weight of 20 kilowatt hours now. We already know the 20 is not quite enough, and we're doing the testing to ensure that we have enough juice to make it across the puddle. But it'd be really interesting if we could get that weight gain and get some information on this product out there. Anyway, so that's it for our early 2014 update. We've got a lot of cool stuff coming. I think you guys do too. So keep building, we'll keep building, and we'll catch you soon. Thanks a lot.